We're continuing our investigation into electric and magnetic fields by looking at cathode rays. And the safety here, you've got high current and a very high voltage. So caution and teacher demonstration only. Do not touch the apparatus once it's been turned on. And because there's a near vacuum in the flask, there's a danger of implosion, so wear goggles, and for the students too as well, please. And some features of the tube. There are several of them. We'll look through them with a bit of detail. The grid in the middle has zinc sulfide coating on it, so it fluoresces when the cathode ray hits it. The glass vessel is sealed and it's at very low pressure, almost a vacuum. And we have the phosphor-coated screen, which will glow as we're in parts when we're doing the experiment. There's a metal cathode. It can be any metal, going to be heated to produce the stream of electrons. Here's the Electron Gun, which includes the cathode and the anode, are often cesium atoms with a single valence electron. And you can pause here to look at the particular features as they are labelled. And we're going to look at the properties of cathode rays. And to start with, they make a phosphor screen glow. The cathode rays itself isn't visible, but when it hits the screen, here it's seen as a blue line. External electric field will affect the cathode ray, as will an external magnetic field. And so we're going to look at that today with an experiment with the magnetic field. And so with no magnet, the cathode ray tube just has a straight line on the phosphor screen. Check the magnet's polarity with a gimbaled magnet. And here, the south pole of magnet is away from, out of the influence of the cathode ray. And when brought closer, we've got a deflection downwards. And pause to work out, is that expected with Fleming's left-hand rule? And the diagram of what you see there with a deflection. And if we move the north pole of a magnet, here it's beyond the sphere of influence, and when we bring it closer, and we get an upward deflection. We're going to have a look at a video of the lab with the magnetic field affecting a cathode ray.
A wire from there to there, a little coil of wire in there, and it's in a vacuum. Good vacuum, not bad. And this is really just one step on from Edison's light bulb design. A nice filament glowing in there. And all we have to do between the end here, technically, I've actually only got it from there to there, is about 5,000 volts. 5,000 now. And that is enough around here. If you imagine a glowing wire, the wire shakes sufficiently to actually cause electrons to leave the surface. It gives them enough kinetic energy to overcome the work function, they leave the surface, and they form a space cloud around the hot cathode. And then, a huge potential difference here, the equivalent for charges of a big slope, is whisked away, and then they hit this fluorescent, whatever this is, piece of metal or plastic in there. Looks like plastic. And they cause the surface to fluoresce, to give off light that you can see, because you can't see the electrons. Now what's interesting is you can deflect this electron beam. This sorry piece of technology led to the invention of the television. All you had to do then was aim this beam at various places on the screen while tracking it back and forth, turning it on and off rapidly, and you could get places on the screen to fluoresce, red, blue, green fluorescence, not just blue, and you could create moving pictures with it. That was the basis of the TV. When I grew up, TVs were about as complicated as this too. They have changed since. So, all this, which is really cool. Now, there are fancier ways you can do this. This thing comes with magnets both sides that give you a stronger field, but magnets are so good these days, you can just bring them forth like this and it's fine. Okay, so let's check this out, see if it works. My contention is this is a beam of invisible electrons being shown up by hitting something and glowing blue. Here's on here, south again. How would I check this is the south end? You take it for granted, I've written S on here.
If it deflects or trapped, like whether the electrons are repulsed or...
No, it's simpler. Pass me the gimbal magnet thingy. Let's try that. This is our, okay? So, we agree? Mm-hmm. That's the south end, the north end. All right. So, this is south. So if I put this here, which way is the field cutting across there? Towards the magnet or away from the magnet? Towards, right? It's going that way, from north to south. So it's cutting this way. Okay. And we've got a downward deflection. Which way is conventional current? If electrons are going that way, which way is current?
That way.
Right. So, current's that way. The field, hang on, which way is the field? Current's that way, rather. That way. The field is, current's that way. The field is towards you. And my thumb is pointing down. Consistency in current. So,
and pause to get the link here. And also looking at an electric field, but an external, in addition to the electrical circuit that's producing the cathode rays themselves. And so above and below the grid, we've got the positive and negative terminals of a external circuit. So, cathode ray is deflected upwards towards the positive, and it's being deflected away from the negative pole. This is what you would expect if your cathode ray is a stream of electrons. And pause to get the link to the animation. Also, cathode rays are blocked by a solid object, and the first time the experiment was done, it was done with a Maltese cross, this particular shape, and it's going to be suspended in the center of the cathode ray tube, and to the left side on the curve of the round bottom flask, there's a zinc sulfide screen that's on the inside surface of the cathode ray tube. And when the circuit's turned on, the high voltage supply, you actually get a shadow. The object that you put in, and it can be any shape, here the Maltese cross, blocks the cathode ray tubes. Where the cathode ray goes outside of it, it's not blocked. And here we want to solidify your knowledge, describe why a cathode ray tube moves when a magnet approaches, what's going to happen if it flips, and how could you alter the amount of deflection, make it greater, make it smaller. Pause to answer those questions. And with many thanks to Washington International School Team Science, in particular Mr. Godwin and his 10th grade physics students.